I'm going to go through an example problem of rolling on an inclined plane. There's a few different ways we could approach this problem. We could do it in terms of just kinematics, where there's a constant acceleration while this cylinder is rolling down the roof, and then it's in free fall until it hits the ground. And then once we know the speed of the center of mass at the last point in contact with the roof, we could turn that into an angular velocity. So you can do it that way. I'm going to do the problem in terms of energy. So I think it's a little bit cleaner, and I always just like energy better. So what we have a cylinder of radius 10 centimeters, 12 kilograms, so pretty hefty. It's a uniform cylinder, so its rotational inertia is a half mr squared. So that's saying that this dimensionless prefactor is a half. It rolls for 6 meters along the roof. It falls 5 meters to the ground, so it's a pretty tall roof. And this angle is 30 degrees. So it's a pretty steep roof too. So good for a physics problem, not necessarily the best for a house. All right, we want to find two things. How fast is this cylinder rotating about its center when it leaves the roof, and where is it going to land? We can assume that the ground is level. So proceeding from conservation of energy, all the gravitational potential energy in the initial state when it's at rest is going to be kinetic energy in the final state. And so I'm calling when it's there as initial, and when the cylinder is about to break contact with the roof, that's what I'm taking to be the final state. Okay, so U initial is K final. Initial gravitational potential energy, we need to know how high up it is. So that's going to be mgl sine of theta. So the height of this point is equal to the hypotenuse times sine of theta. And then kinetic energy, we need to remember that we have two kinds of kinetic energy in translation and kinetic energy in rotation. And I'm going to plug in what the rotational inertia is for the uniform cylinder. I've got a half m with a smooth rolling condition. The speed of the center of mass is going to be omega times r, so v squared becomes omega squared r squared. Fill in what the rotational inertia is. We have beta m r squared omega squared. And every term has the mass in it, so gravitational mass is canceling out with inertial mass. And multiply both sides of the equation by 2. 2gl sine of theta is going to equal omega squared r squared times 1 plus beta. Omega squared 2gl sine of theta over r squared 1 plus beta in parentheses, and then take the square root of both sides. We're looking for a speed, so I don't care about the roots. I've got a 2 here on Earth, presumably, 6 meters, sine of 30 degrees, which is a half. R squared gives me 0.1 meters quantity squared, and this gives me 1 plus a half, or 3/2. It's all under the radical, and that gets me 62.6 radians per second in the final state. And then the final speed we can get once we know omega, and we'll need that to answer the second part. Where is the cylinder going to land? It's a projectile motion problem with a known initial velocity with x and y components. So omega times r, just shift the decimal point, 6.26 meters per second. Okay, now, make sure we have coordinates for the projectile motion problem. So I'm going to pick x to go to the left and y to go straight up the page. We can write out the initial velocity vector and then start doing our kinematics game. We'll have initial velocity vector right when it leaves contact with the roof. I'm going to have 6.26 meters per second times cosine of 30 degrees along the x direction. Then it's falling down initially. So minus 6.26 meters per second sine of 30 degrees along the y direction. And then multiplying that out, you have our initial velocity plus 5.42 meters per second along x, and then minus 3.13 meters per second along y. All right, so we know how fast the cylinder is moving when it breaks contact with the roof. We can find where it lands. And with kinematics, there's always like more than one way to do it. I'm gonna pick a way, but you could use different equations. You'd still have the same physics. So if I use the y component of the equation of kinematics without time, final y velocity squared is initial y velocity squared plus twice the acceleration times the displacement vertically. I'm going to use that to solve for final Vy, so the velocity right before when the cylinder hits the ground. So I'm going to have a minus. This is going to give me a 3.13 meters per second quantity squared plus 2 times minus 9.81 meters per second squared, and then 5 meters. It's the height of the roof. It falls 5 meters. That's all under a radical, minus 10.39 meters per second. And I can just go through and ignore the positive root because we're concerned with the cylinder falling down. Once we have the final vertical velocity, we know the vertical acceleration is due to gravity, so now we can find the time. So delta V over final time is equal to the vertical acceleration. So we have the time that is in the air minus 10.39 meters per second. Just coming from there, I'll have a minus minus, which is a plus, 3.13 meters per second. And we picked up to be the positive direction, so I've got a minus 9.81 meters per second squared, which this is going to give me a time of 0.74 seconds. And then lastly, how far over was the x coordinate where it lands? Well, it's not undergoing any acceleration left-right, so we just have the initial x component of the velocity times time. So 6.26 meters per second times 0.74 seconds. So they give me 4.63 meters plus. So we can say the cylinder will land at x equals plus 4.6 meters, and then that is where we picked the 0 for our y coordinate to be. So y equals 0. And there we go.